So in this video, we're going to talk about some properties of limits and then end with finding the limit of a difference quotient. So if we want to define some properties of limits. So we're going to let f and g be two functions, and we're going to assume that the limit as x approaches c of function f exists, and it goes to this value called L. And the limit as x approaches the same number, c, of g of x exists and approaches some number m. L and m are going to both be real numbers. So first property says that if we want to take the limit as x approaches a number c of some constant value, we're just going to get that constant. That's looking at the function maybe like this. Maybe this is the function y equals 3. And I ask you, what is the limit as x approaches the number 2 for that function y equals 3? Well, here's the x value of 2. As I come in from the left and from the right, I'm going to approach that number 3. That's what that property is saying. Property 2 is looking at the function y equals x. If we take the limit as x approaches c of x, then we're going to just get the number c. So we know y equals x looks like this. So let's say we are looking at the x value of 1. Suppose I ask you, what's the limit as x approaches 1 for the function x? Well, we know if we just plug 1 in, we're going to get 1. That's because the point 1, 1 is on the graph of y equals x. So that's why that's going to happen. It's going to be just whatever the x value is for any single point on that graph, y equals x. Property 3 says the limit of the sum is equal to the sum of the two limits. So if I know what the limit is for f of x plus g of x, that's the same thing as I know this and I know this, and we actually knew those from up here. So then we could find this limit just by finding applying what we know. The limit as x approaches c of f is L, and the limit as x approaches c of g is m. So we could just add those two limits together. Same thing works with subtraction. The limit of the difference is equal to the difference of the limits. So we would just subtract those two numbers. And then we have a scalar multiple property that says if I want to take the limit of some number times f of x, then if I know this limit as x approaches c of f of x is L, then all I have to do is multiply it by whatever that scalar value is, k. Property 6 says the limit of the product is equal to the product of the limits, so we just multiply those together. 7 says the limit of the quotient is equal to the quotient of the limits. That works as long as we're not dividing by 0. If we're dividing by 0, we have problems. And then property 8 says if I take the limit as x approaches c of the nth root of f of x, I could take that limit of f of x first, and then I can take the nth root of that limit, whatever that number is. So let's apply those properties. We're going to apply those here. Let's look at 39. The limit as x approaches 1 of negative 3 times f of x. That's the same thing as saying negative 3 times the limit as x approaches 1 of f of x. And we know what that limit is. They've told us is equal to negative 5. So this whole piece here is equal to negative 5. So we're going to have negative 3 times negative 5, which is a positive 15. So there's our final answer. Now let's look at 40. We could rewrite this, kind of pull that 2 to the front, because we have a property that says we can do that. And then we know what the limit is as x approaches 1 of g of x. They've told us that's equal to 4. So we're replacing that whole thing by 4, and that's going to give us an 8. So now let's look at 41, and I'm going to come down here and write this. We have the limit as x approaches 1 of 2f of x plus g of x. We want to find the limit after we do that. Well, we can use those limit properties to rewrite this. We could rewrite this as the limit as x approaches 1 of 2f of x plus the limit as x approaches 1 of g of x. And then we could rewrite this first one as 2 times the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. So now we know what the limit is as x approaches 1 of f of x. That's equal to a negative 5. And then for g of x, we ended up with 4 because they gave us those up here. So we have negative 10 plus 4, which is a negative 6. Let's look at 43. So 43 is asking us for the limit as x approaches 1 of 2 minus f of x over x plus g of x. So we could write that as this, taking the limit of the top and the bottom separately. I'm going to use brackets to show I need to take the limit of each piece. But that's the same thing as taking the limit as x approaches 1 of 2 minus the limit as x approaches 1 of f over the limit as x approaches 1 of x plus the limit as x approaches 1 of g of x. So we know some of these pieces. The limit as x approaches 1 of 2, that's a constant function, so it's just going to be the number 2. The limit as x approaches 1 of f, they've told us was negative 5. That was here. The limit as x approaches 1 of x is just going to be equal to 1. And the limit as x approaches 1 of g of x, well, they've told us what that was, and that was equal to a 4. So we're going to get 7 over 5 for that limit. And I'm going to do one more of these. Let's look at one with a square root. Let's look at 45. They're asking us for the limit as x approaches 1 of the square root of g minus f. So we know we could take that square root outside and take the limit as x approaches 1 of g minus f. And we could rewrite that. The limit of the difference is the difference of the limits. Now let's substitute in what we know. We know the limit as x approaches 1 of g is 4. And as we approach 1 for f, we get negative 5. So we're going to have the square root of 9, which is equal to 3. So there's our final answer. So we can use those properties to help us figure out some limits if we don't know really anything about the function and all we know is what the limit is defined to be at a couple of values like here. The last thing we're going to talk about in this section is the limit of the difference quotient. And this is actually a really important concept in calculus because it's going to take us into this idea of what the definition of a derivative is. So I'm actually going to take this just a step further and talk about what the limit would be as h approaches 0 of f of x plus h minus f of x, all divided by h. And let's just look at it in an example. Let's say we have the function y equals x squared plus 2x plus 1. And we want to apply that difference quotient. And then take the limit. So if you remember, we broke this down into a few steps before. Our first step would be to find f of x plus h. So to find that, we're going to substitute x plus h in for every x into the function. So we're going to have x plus h squared, plugging in there, plus 2 times x plus h, substituting in there, and then plus 1. If we square this, we have x squared plus 2xh plus h squared plus 2x plus 2h plus 1. So we found this piece. Step 2, oops, I forgot to put the 1 there, is to find the numerator, f of x plus h minus f of x. Okay, so that takes what we just found and subtracts the original function, x squared plus 2x plus 1. So notice if we were to distribute that negative, the x squareds and the 2x's and the 1's are going to cancel. So we're left with 2xh plus h squared plus 2h. Step 3 of the difference quotient is to take what you just found and then divide by h. So we're going to have 2xh plus h squared plus 2 and divide by h, 2h. Now notice every term in the top, we could factor an h out. And if you notice, those h's are going to cancel. So we're going to get 2x plus h plus 2. So there's our difference quotient. But this is taking it a step further, and now we want to find the limit as h approaches 0 of that difference quotient. So we're going to take the limit as x approaches 0 of 2x plus h plus 2, and that's going to give us 2x plus 2. Okay. Now, what is this used for? This is actually the idea behind a derivative, which we will talk about more in depth in a couple of sections. But just to give you a brief overview of what's going to happen, that will actually tell you the slope of the tangent line for this function at any point. So if we were to do a quick sketch of that graph, it would look something like this. Quadratic opens up. Tangent lines are lines that touch the graph at one specific point. So that would be a tangent line. But notice those slopes are going to change as we move along that graph. Down here, where it touches that x-axis, we would have a slope of 0 for that tangent line. And then slopes are going to be positive on the right half of the graph. So what this does is it finds the slope of the tangent line at any point along the graph of that function, x squared plus 2x plus 1. So we'll talk more about those later, but that is a good introduction to what the idea of a limit is. In the next section, we're going to talk about infinite limits.